So what these do, what contrast injectors do is they basically make it possible for blood vessels to show up on images. Perfect, thank you. Now, how does anybody in here have absolutely no idea how imaging works as far as taking an X-ray and how X-ray images are produced? Okay, so everybody has some idea in that. So good starting point. So let's say this is my X-ray table, okay? Patient's on the table, we have an X-ray tube up here. I actually taught X-ray for about 6 years when I was with Ditech. So patient on the table, X-ray tube up here, and underneath the table or inside the table, there's gonna be some image capturing device. Back when I first started teaching, it was film. Now it's all digital plates. Is there any film left in radiology? I know dental does, but any film left? Anybody still shooting film? I didn't think so. It's all digital. All right. So how this works, all right, X-rays come out of the X-ray tube, and for our sake, this isn't 100% true, but for our sake, 100% of the radiation comes out of the X-ray tube, goes into the patient, all right? Now, some of the radiation goes into the patient, is gonna penetrate through the patient and strike that imaging capturing device that's underneath that table, all right? And some of the radiation that goes into the patient is gonna be absorbed by the patient and just get absorbed and dissipate and never come out, all right? So we have penetration and we have absorption. To get an X-ray image, you need both things to happen, all right? Some of the radiation has to get blocked by the patient. Some of the radiation has to go all the way through the patient and hit that imaging plate. Now, the reason for that is, as X-rays strike that plate, when X-rays strike that plate, the area of that plate that gets struck by the X-ray photons starts to turn dark. And the more X-rays that strike it, the darker it becomes, okay? So it basically starts off as a clear image, and then as X-rays strike it, it makes those parts of the plate darker, okay? Now, the odds of, or whether an X-ray photon is gonna penetrate a patient or not is determined by the body part that X-ray photon interacts with. Now, the thicker and denser the body part, the more likely that body part is to just absorb that X-ray photon. The less dense and the less or the thinner that it is, it's more likely that X-ray photon will pass right through. So if you think about it, your typical radiographic image, it's a black background, and then let's say it's a chest X-ray, you can see all the ribs and everything, and all the bones are white. That's because the bones are thicker and denser than all the soft tissue in the body, so the bones actually absorb the radiation. So those parts of the plate that are shielded by the X-ray photons from bony structure don't get any radiation. So that part of the plate stays white or nearly white. But then the soft tissue that lets the X-rays pass through it, those photons pass through the patient, strike the plate, turn those areas dark. So that's why the background is dark and then the bony structure is white. Everybody understand? Okay, now, blood vessels are neither thick nor dense, all right? X-ray photons, even a weak X-ray photon has no trouble passing right through a blood vessel, all right? So that's why blood vessels don't show up on X-ray images, because they're not thick or dense. They just get blended, they just get blacked out, all right? Which most of the time the doctors don't care. Get an X-ray done, we're looking for broken bones and stuff like that. But sometimes there are instances where we do want to see the blood vessels, all right? That's why we're doing this. Now, if we're gonna do that, then we have to put something in the blood vessels that will make the blood vessel absorb radiation. And that is a specific kind of fluid. It's called contrast fluid, and that's the fluid that are in these syringes here. Contrast, we're not really gonna get into it, but due to the makeup of contrast absorbs X-rays, and it's really, really good at it, all right? So if you put even a minuscule amount of contrast in a blood vessel, that blood vessel will now absorb the X-rays, and now that blood vessel will show up real nice and bright on the X-ray image. So that is the whole purpose of the contrast injectors. That's why they're called contrast injectors. An image, the difference between how dark an image is and how bright it is called contrast, the difference in white to dark. And that's why these are called contrast injectors, because they increase the contrast of the blood vessels on the images. All right? All right, everybody clear? Cool. All right. Johnny. Oh, yeah, you're kidding me. Do this old-fashioned way. All right. So what I just described to everybody is referred to as angiography. All right, I don't know. It's referred to angiography. Angio is blood. Ography means the viewing of blood vessels. Angiography is performed to view blood vessels better after injecting them with a radiopaque dye, or the contrast fluid that outlines them on the X-ray. Now, everything I just described, this probably isn't the best first image to show up, because that scenario I just described to you was a radiographic image, which means that your typical lay on the table, X-rays through the body, shows an image. This is actually a fluoroscopic image. which is a little different. That's why the background is white and the blood vessels are actually dark. It's the same exact concept, just in reverse. All right. Now, there's approximately probably 18 or 20 different models of contrast injectors that are in general use throughout the world. Here in the United States, it's about 15 different models that are actually in use. We do training on 12 of those models. Some of the models are just really old and they're still around, but we haven't never developed training on them. But it doesn't matter what kind of or how many different models there are. Each one can be broken into one of three types. There's three kinds of contrast injectors. There's CT, MRI, and angio. Now, I always tell my students, all contrast injectors, they're like defibrillators and infusion pumps in the sense that you've seen one, you've seen them all. They all do the same way, the same thing, the same way. And it's just a pump. And I mentioned that to him back there. It's a pump. It's a fancy pump. It's a high-end pump. But at the end of the day, it is just a pump. So same thing. If you get trained on how to operate one or maintain one, you can generally do all of them. You can walk up to any contrast injector on the planet and know how to operate it because it's, they're all basically the same. Now, each one is going to have its own little bell or whistle or feature that's kind of unique to it. And each of the three types, CT, MRI, and angio injectors, they are slightly different due to the modality they're being used in. But for the most part, like I said, 95%, they're all the same, with one exception. There is one contrast injector model that's just, man, I don't know. It's the ACES CVI. It's not a bad injector. The ACES CVI is it's like the engineers that made the ACES CVI. It's like Bracco went to all their engineers and said, who here has never seen a contrast injector in your life? And all the engineers that raised their hands like, all right, you four guys, just go make up a contrast injector. And they came up with the ACES CVI, and you can tell. It works fine, but man, it is nothing like the rest of them. Nothing like the rest of them. It's the Siemens of contrast injectors. Any Siemens people should have asked first? No. All right. So, button work. There we go. So, angiography. Each of the systems uses the contrast injector to inject contrast medium into the patient to improve, or in some cases, make it possible to view the blood vessels. The images produced are referred to as angiograms or angiographs. Now, CT and MRI injectors, and this is always true. CT and MRI injectors, the contrast is always injected into the patient with an IV needle, and the IV needle can go on the hand or in the elbow or whatever. Angio injectors, the ones that are used in your typical X-ray rooms, your cath labs and your IRs and stuff like that, those always use a catheter, and the catheter will be anywhere from 2 to 3 feet long, roughly, and it usually gets inserted. It can get inserted into the carotid, but they'll typically go into the femoral artery or femoral vein, depending on the body part they want to snake the tip of the catheter to get the contrast into that spot. The most common, by far, the most common purpose of a angio injector is images of the heart. So they'll go into the femoral artery and snake the tip of the catheter up into one of the chambers of the heart, or the femoral vein if they want to go to the other side of the heart. The contrast is just later. In the next 12 to 24 hours, typically the contrast that is injected is just filtered out through the system's kidneys and liver to just get rid of it. All right. Now, in the United States, there's three manufacturers, and there is an absolute pecking order amongst the three. Bayer Medrad is by far the biggest manufacturer of contrast injectors on the planet, but here in the United States, probably 90% of all contrast injectors are Bayer Medrad injector. Great company. They're very good injectors. They're just really expensive with their service contracts and stuff like that. The second biggest company, bad editing. The second biggest company, and I'm not saying second, like way behind in second, but definitely second, is Guerbet. Used to be Covidien, used to be Mallinckrodt, used to be Tyco, used to be Levoflorsheim. I even left some out of there. Tyco, Covidien. Yeah, I haven't even updated that. It's not even Tyco anymore. It's Guerbet. They also make very good injectors, but they're less than 10% of all contrast injectors in the United States. And then third, but making a rapid ascent is a company called Bracco. They make the ACES and the Empower injectors. They're the ones that make that ACES injector that I said is the weird one. Their Empower injectors, the Empower CTs and MRIs, they're normal injectors. I don't know why they just went crazy with their angio injector. Excellent injectors as well, very good injectors, but any Bracco people in here? Okay. very good company, very good injectors, but they do not work and play well with others. They won't sell you anything. They won't send anybody out to you if anything breaks. They won't sell you any parts, anything. And I mean, anything goes wrong with your Bracco injector, they make you send it in, box the whole thing up. A power button, literally, there's a little plastic orange, but they won't sell it to you. Now, if you're in good, there are some Bracco service reps in the cities that if you're in good with them, they'll just, yeah, here you go, stuff like that. But yeah, in general, again, nothing wrong with the company. They're very, very good injectors. But yeah, they don't work and play well with others. Like I said, however, there are a couple of companies that we deal with that when someone goes through our training and they've been trained on how to do the maintenance and repairs on these things, when they go out in the world, they need help, they need parts. There are 3 companies that we always recommend to the students. If you need a part or tech service, tech support, anything like that, check one of these 3 companies. There is one of the companies that's called IMED. It's out of Texas. They do specialize in the Bracco injectors. They have some service guys who are service trained on Bracco models, and they do have parts and great tech support for the EZM injectors, the Bracco injectors. All right. There is a 4th company that's really big. It's called Ulrich. Huge in Europe and Asia, but not so much here in the US, although they have started to get into the US market. They are starting to show up here. It's a crazy injector. I won't get into it, but I don't know how it works. I mean, I know how it works, but these are all piston pumps. The Ulrich injectors, if you guys know your biomed real well, they use peristaltic pumps, which I'm like, I don't know how you get those flow rates and then consistent flow rates and volumes with peristaltic pump tubing. And if you know peristaltic pumps, you got to swap the tubing out regularly, like weekly or monthly like that. And the operators have to do that. I don't think, but I mean, GE, I think is, yeah. When GE now on their new CT installs, did they do with the MR as well? Yeah, they're it's an Ulrich pump, right? Yep. So GE is trying to introduce Ulrich into the United States. So we will see how it goes. We'll see how it goes. It just plugs into the wall, right? It's all one set, like a portable ATM machine. Yep. All right. Now, the contrast, intravenous contrast highlights the blood vessels, so you can see here how well it works. So this is actually an image of the heart. The heart is about the size of your fist, and then this big blood vessel right here, that's the aorta. That's the main artery that comes away from the heart, and that's roughly about the width of your thumb. So you can see here, the heart in the background nearly is blacked out, so there's no contrast, almost no contrast in the heart at this particular moment. All the contrast has been pumped into the aorta. So the heart is much bigger and thicker than the aorta, but in this particular instance, there's no contrast in the heart. All the contrast is in the aorta. You can see how brightly the aorta shows up on the image versus you can just make out the back of the heart in the background there. So just an example of how effective this contrast fluid is. Once contrast is injected into the patient or into the bloodstream, it circulates throughout the body. And that's one thing that some procedures, the operators, the technicians do have to be aware of. So it's primarily with not CT and MRI injectors, but angio injectors. When we inject contrast fluid into a patient, I want to see the image of the right ventricle or the left atrium or whatever. When we inject that fluid into the patient, there has to be some timing with the imaging system because this is a living patient, and as soon as that heart beats, that fluid's moving, all right? Heart beats 1 second later, it moves again. So we have a very, very less than a second short window of taking these static images of a particular body part if we're using the contrast injector for an angiographic procedure. MR and CT injectors is just done with an IV. So basically we're just kind of flooding the whole patient, not 100%, but that's the gist. We're flooding the patient's bloodstream with contrast so we can see it everywhere. It's not 100% true, but it's generally true for this class. The X-ray beam passing through the patient. We only got an hour. The X-ray beam passing through the patient in the case of X-ray and CT, or the RF pulses emanating from the patient in the case of MRI are diminished, therefore making those particular anatomical structures show up as brighter images on the image, as brighter objects, region of interest on the image. All right. Now for X-ray and CT are both use X-ray tubes. All right, so the images are produced with radiation. So for both X-ray and CT, it's basically the same recipe. The contrast fluid is the same. The main ingredient in a contrast fluid is actually iodine. All right, iodine, and I don't know why. It's due to the atomic structure of iodine and how many electrons are in the orbital shells of it. But iodine, for whatever reason, is excellent at blocking X-rays. So when they put iodine into the patient, that region of interest, that area blocks the X-rays. So iodine is the main ingredient in the contrast fluids for CT and angio procedures. Now for MRI, wrong button. MRI does not produce images with radiation. So iodine does absolutely nothing to an MRI image. MRI is produced with RF pulses and a magnetic field working together. So for MRI procedures, they have to use a different kind of contrast fluid, and that's called gadolinium. Without getting into it, basically gadolinium weakens the RF pulses that are emanated from the patient during the actual X-ray procedure. Same exact result, just does it in a totally different way. So CT and angio injectors have iodine-based contrast fluid. MRI has gadolinium-based contrast fluid. And I don't know how gadolinium does what it does to the hydrogen atoms in the body. It just does, though. All right. Now, getting into the actual machines. All right. So before I tell you that, I got to tell you this. All right. So I don't know how well. All right. So do my best here. So for you guys to see it. So over here, this is the display. Now, whenever we're going to do an injection into a patient, there's three things that the operator has to select. There's three parameters that they have to select. There's a bunch of others, or several others that they can select, but there's three things that have to be picked: the flow rate, the volume, and the pressure limit. Now, the flow rate, all right, that's the speed of the injection. How fast are we going to force this fluid into the patient at a milliliters per second rate, all right? Then the other thing they select is the volume, all right? So we picked how fast we're going to inject it. Now we need to decide how much we're going to inject into the patient. And it can be anywhere from 10 to 100 milliliters, if not a little bit more. Those two are obvious, all right? Now, the third thing is something called pressure limit, all right? Now, this is an important safety feature, and it's sort of a patient safety issue, but it's more of an injector safety issue. Pressure, whenever we do an injection, let me go and throw these on. Whenever we do an injection, there's going to be pressure built up in the syringe during the actual injection, because this is about a 1.5 inch wide syringe, and then it's going to get down to about a 2 millimeter opening, and then there's going to be this connector tubing. Do I have connector tubing? Wrong connector tubing. So then there's going to be connector tubing that, and I'm not going to connect it all the way. No. One for each syringe, and I'll tell you why there's two syringes here shortly. Just like that. And then the connector tubing here goes to the patient. All right. Now, so whenever there is an injection that takes place, so we have this connected to the patient, and this is shoving fluid out. There is a very long, thin tubing here that the fluid also has to get shoved through. And then once we get to the patient, it goes into a little IV needle, which is either a 20 or 20 probably a little big, 22, 23, 24 gauge needle, if not smaller. So an even smaller opening. So we're trying to shove fluid out of this syringe through a really tiny little IV needle. There's going to be a lot of pressure built up behind it. All right. Now that pressure buildup is in the syringe. All right. It's not in the connector tubing. It's not at the patient. All right. So for typical CT and MRI injectors, it's 300 psi is the typical pressure limit that they're asking for. All right. 300 psi. Now again, that is not in the patient. That is not in the patient. All right. If you guys are BMETs, if you work on infusion pumps, the occlusion alarm for infusion pumps is typically what, 12 psi, 10, something like that. Yeah, very, very low. I mean, so on an infusion pump, if it hits like 10 or 12 psi, man, it shuts off, but not shut off. It stops the infusion, alarms go off, nurse call goes off. So, but that's for an infusion pump. So no, 300 psi, that pressure limit, that is saying in the syringe, don't exceed 300 psi in the syringe. Okay. Now, and again, this is just fluid dynamics a little bit. Well, it's all fluid dynamics. It's 300 psi in the syringe. Once we get to this little tiny opening, there's a dramatic drop in the pressure. We literally go from 300 psi to single digit PSI. And the closer we get to the patient, the lower and lower and lower the pressure gets. By the time we get to the patient, the fluid is actually coming out in the patient's vein or artery, we are in the low single digits. All right, so that 300 PSI is not, no, of course we're not gonna put 300 PSI of pressure in the patient. And some operators don't understand that. They get worried. They'll like, ooh, 300 PSI, let's lower that to 200 PSI or something like that. That's just gonna cause problems. Now, and I'll go ahead and bring this up now. So we're doing our injection, all right? We've set the pressure limit to 300 PSI. And let's say for whatever reason, during the actual injection, we do get 300 PSI. Now, let me back up one more second. When we do the flow rate and the volume, all right? Flow rate of 10 milliliters per second, a volume of 20. Those are the goals. We want a flow rate of 10 milliliters per second. We don't want anything up to 10 milliliters per second. We want a flow rate of 10 milliliters per second. And if I say I want to inject 20 milliliters of fluid into the patient, we're going to inject 20 milliliters. We're not going to stop at 19. We're not going to go to 21. We do 20 milliliters exactly, and we're done. All right. Now the pressure limit, that's not the goal. All right. The pressure limit is just saying don't exceed this. Anything below this is perfectly fine. As a matter of fact, most of your shots are going to be double-digit pressures. All right. It's relatively unusual for CT and MRI injectors. For just CT and MRI, it's relatively unusual to get over 100 PSI. In the syringe during a CT or MRI procedure. Angio injectors, a little different animal, you'll get higher pressures, but those go higher. Angio injectors, CT and MRI injectors go to 300 PSI, angio injectors go to 1,000 or 1,200 PSI. It's just due to the nature of the beast, it's how it's used. All right, so pressure limit, that 300 PSI, that pressure limit is what's in the syringe and it's not in the patient. And it's not a failure, the injection didn't fail. We don't get our 300 PSI or whatever we set it to, okay? Now, one more thing, and then we'll move on. Let's say we do hit our pressure limit, all right? So I just talked about infusion pumps, when they hit their pressure limit, their occlusion pressure, whatever they refer to it as now, it stops, the infusion pump stops, all right? That is not the case with contrast injectors, all right? If we hit our pressure limit, let's say we've set it to 300 PSI, and during the injection, we hit 300 PSI, the injector sees that, it does not stop the injection. And the reason for that is, all right, we're here in the x-ray room. Besides contrast fluid, what else are we firing into the patient at this particular second? X-rays, all right? The injector stops. We got to do this again, which means now that was all wasted dose into the patient. So if the injector hits its pressure limit during the actual procedure, it doesn't stop the injection. Well, what it will do is it will slow the injection down, because the primary determinant of how much pressure gets built up in the syringe is the speed of the injection, the flow rate. The faster the injection, the greater the pressure that gets built up in the syringe. I mean, if you think about it, this is a 200 milliliter syringe. Let's say I wanted to shoot all the fluid out of this syringe in 1 second. 200 milliliters per second is not an option, but let's say it were. We're going to shove all this fluid out of this little tiny hole in 1 second. That is going to be a huge amount of pressure built up in the syringe. But now let's say I want to shoot this 200 milliliters over 1 milliliter per second. So now it'll take, instead of 1 second, it'll take 200 seconds to get all the fluid out of here. That's a much slower injection. That's barely a trickle, obviously much lower pressure built up in the syringe. So there's a few other things that do affect pressure in the syringe, but the primary determinant is the flow rate. The higher the flow rate, the greater the pressure in the syringe. So if my system does hit the pressure limit, it doesn't stop the injection. It just backs off on the flow rate to keep us from going over the pressure limit, all right? Because it might, I mean, we're shooting a flow rate of 10 milliliters per second. It might only need to back off to like 9.5, okay? We'll still probably get a good image. But if the system shuts off, we definitely won't get an image. So we definitely have to do it again. We might have to do it again anyway, but even if it hits its pressure limit, it doesn't mean it's a failure. We still might get good images, useful images out of this procedure, and then we don't have to hit the patient again. All right. Any questions? All righty. These next few slides is everything I just talked about. Protects the syringe. This is the primary thing. The pressure limit is basically there to keep the syringe from rupturing during the actual injection. Now, it doesn't explode like a grenade. It'll typically crack, and then contrast will leak all over. It's bad, but it's not. It's protecting the patient sort of, but it's more protecting the equipment than it is the patient, because the equipment's not getting there. Now, little thing, it's not in the book or up here, but there is a difference between a pressure limit and an occlusion. All right, a pressure limit, we still have flow. We've just gotten too much pressure during the actual injection. An occlusion is different. An occlusion is we have a blockage and the system's trying to push and we're not getting fluid coming out of it. it does treat an occlusion differently. If it senses an occlusion, it does shut the injector off, right? It does stop the injection, right? So an occlusion is treated differently than just a pressure limiting event. Yes. Mm. Well, just well, no, I mean, it's just, well, let me put it this way. If there is an occlusion, all right, let's say we have a blockage. So let's say somehow the end of my connector tube or the end of the IV needle is completely clogged. If I have 300 PSI here and there's an occlusion down the line, there is 300 PSI from here all the way out, okay? But, so that's why on an occlusion, it will stop. But there's nothing that it's doing to monitor the pressure at the patient. It's just monitoring the pressure in the syringe. So if it knows if we still have fluid flow, and the way it knows we have fluid flow is if the motor's turning, then we have flow, all right? It may be really high pressure, but if the motor's turning, because liquid can't compress, fluid doesn't compress. So if there's an occlusion, the motor can't compress the liquid. So if the motor stops turning during an injection, it knows this is an occlusion, let's stop the injection. But there's nothing really monitoring the pressure in the patient. It just knows that if we have pressure here, then it knows if the motor's turning, we have flow, which means there's basically no pressure from here to the end. Yep. All right. Other things that affect pressure. I said the primary thing that affects how much pressure gets built up in the syringe is the flow rate. That is 99% of the ballgame. But the other things that do also affect how much pressure gets built up in the syringe is the length and the width of the connector tubing. The longer the tubing, the more tube we have to shove through it. So it's going to be slightly higher pressure. The thinner the tubing also affects how much contrast or the pressure that gets built up in the syringe during the actual injection. And the last thing is the viscosity of the fluid. Now, contrast fluid, it is clear, which I think is silly. If I were in charge of the world, never mind, I was about to say something. Nope. If I was in Doji, I would tell the industry, you gotta put some color in your contrast fluid, because every year it happens. It's a 1 in 10 million thing, maybe more than that, but every year somebody gets killed by a contrast injector, and it's usually the Stellant. And not because there's anything wrong with the Stellant, it's just the Stellant is by far the most used contrast injector, and it's used over and over. It's used multiple times a day, and there's 2 syringes. But the contrast fluid and the other syringe is saline fluid, which is used for multiple reasons. But contrast fluid is perfectly clear, and so the patient leaves, they pop 2 syringes out, pop 2 syringes in, fill one. Just, it's been a long day. They forgot to fill the other syringe up, and there is no indicator. The machine does not check if there's actually fluid in the syringe. The operator has to say yes, there is no fluid in the syringe. They actually has to hit a button saying I have checked for air. And they did it, and then bang, they just fire an empty syringe into a patient. It happens. It's very rare, but it does happen. So that's why I'm like, let's make it pink or green or something, that I can see from a distance, like, oh, that syringe is empty. But does anybody have Elon Musk's email? I'm not on Twitter or X. All right, don't. All right. Any questions so far? All right, now, contrast injectors. And this is universally true. All contrast injectors have 3 components to them. There is the head, there is the display, and then there is some sort of power unit. All right, all contrast injectors, MRI, CT, angio, manufacturer doesn't matter, model doesn't manufacture. All 3, every contrast injector has those 3 components, and just those 3: the head, the CT, or the head, the display, and the power supply. Now the syringes, yep, I'm gonna take this off. The syringes are model specific. Every contrast injector, with a couple exceptions, there's 2 exceptions, but for the most part, every contrast injector, the syringes are model specific. For instance, this is a Stellant, obviously. These syringes are Stellant syringes. These syringes don't fit on any other contrast injector model in the world, right? And every other contrast injector model is like that. So when we train a student, one of the things we have them do is make sure the first time you go out and do a PM on a Stellant or whatever model, When you get to the department, ask them for a set of syringes. Now the syringes, like all syringes in the United States anyway, some countries don't do this, but the US does. They're one-time use only, all right? This syringe gets used once and it gets thrown out, okay? So the imaging department has literally cases and cases and cases of these syringes, and they're roughly $10 per syringe. They should have no qualms giving the BMet, a set of syringes to do their PM. And I tell the students, now those, that one-time use only thing, that's for patients. That's not for maintenance. You get those syringes from the department, those are now your PM syringes. You keep those. They should last you several dozen PMs before it either cracks during a pressure check, or the tips here where the connector tubing goes to kind of gets worn down. It just won't hold anymore. That's typically why you have to toss them out. But that'll happen during a PM. So if it happens during a PM, just turn around and say, can I need another set of syringes? There's two exceptions. The two of the MedRat injectors, the Mark V Plus and the Provis, have the same exact syringe. And the Bracco units, the Angiometal Lumina and the CT9000, which is ancient, they have the exact same syringes. But those are the only two that I know of that are duplicates of each other. But yeah, so anyway, the contrast fluid. Okay, I'm doing good. The contrast fluid, it's nearly thin as water, but there is a slight syrupy texture to it. Very slight. There is a slight syrupy texture to it. And you know it immediately when you come in contrast. You don't have to worry about it getting on your skin or your clothes. It's literally like maple syrup. Getting maple syrup on your skin, it doesn't do anything, just washes off with water. But as soon as you come in contact with it, it's tacky. Even when it's dry, it's like barely dried paint. It's a little tackiness to it. But there is a slight syrupy contrast, slight syrupy context to it. So what they have to do, or what they don't have to do, what they'll often do, there is a heater, just like this one, all right? Clips on right there. And then this plugs into the back, and this warms up to about 37 degrees Celsius, about body temperature. And what it does is it doesn't heat, it won't warm the contrast up. They can't put room temperature contrast in here and then put the warmer on it and warm it up. But what they'll do is they'll keep the contrast in a warmer, and then once the patient shows up, they fill the syringe, and then they'll slap the heater on, and the heater keeps the contrast warm longer than if the heater weren't on it. Now, a lot of places don't use the heaters anymore because the technology with the CT systems, what used to be a 5-minute CT is now a 15-second CT nowadays. So the patient's not on the table as long as they used to be. So often, a lot of places don't use the heaters anymore because the procedures are over much quicker than they used to be. Some still use them, but some don't. But the purpose of the heater is what happens to syrup when you warm it up. It makes it more runny. It'll flow. It flows more easily. So that's the purpose of the heaters, to keep the contrast warm during longer procedures and things like that. Which also, we were talking about pressure limit earlier. That helps keep contrast, or that also helps a little bit with the pressure built up in the syringe during the injection if we're shooting something that's a little runnier. Now I already talked about these items right here, flow rate, volume, and pressure limits. Dealt with those already. Multi-phase or multi-level injections. So now for CT injectors like this one, you notice there's 2 syringes, all right? So the green side here, this is semi-universal. Not everybody abides by these colors, but most do. The green side over here is contrast, and the blue is saline. Blue is water, so just saline. Some manufacturers stray from those color codes, but for the most part, they mostly stick with that. So I actually have 2 syringes, okay? And you'll notice on my display here, for people who can see it, I have, well, you see the blue and the green. There's my syringes right here. It tells me on the display how much fluid is in each syringe, and the blue syringe is my contrast syringe. The green one is my contrast syringe. The blue one is my saline syringe. But then you'll notice here, I have these 3 lines here, all right? These 3 rows, all right? Now the first row is blue. And so my first column here, so it's the first row is blue, it says 4.5 and 20. So the first column is my flow rate, so I want a flow rate of 4.5 milliliters per second. The second column is my volume, so I want to shoot a flow or a volume of 20 milliliters. And since it's blue, that's my saline syringe. Then we'll go to our second syringe, or the second phase is what we're talking about here, and it's green. So basically what we're telling the machine is, all right, start off with a saline injection, flow rate at 4.5 milliliters per second for 20 milliliters. Then we're going to go to the second phase or the second level, but we're going to switch syringes. We're going to go to the contrast syringe. We're going to shoot it at 4 milliliters per 100, 4 milliliters per second for 100 milliliters. Then the third phase, we're going to go back to contrast and shoot a different flow rate in a different volume. Most contrast injectors, for the most part, they can shoot anywhere from 4 to 8 different phases. 8 phases is a lot of phases. I don't think I've ever seen an actual protocol with that many phases, but that's what it is capable of that. Let me get up. All right, so we're going to make our first phase. We'll make the first phase contrast. We'll do a flow rate of 5, volume of 20, and then we're going to make our second phase saline, same thing, 5 and 20. Enter. So right there, so I have that is a 2-phase injection. First phase is going to be a contrast shot. Second phase is going to be a saline shot. All right. So this, to us, this is one injection, but the injector is going to treat it as 2 separate injections. And what will happen is when we hit the inject switch, so jumping ahead a little bit here, I'm going to hit lock, which locks the protocol in. Then I'm going to hit the arm button. Now, when I hit arm, this is where I mentioned this earlier. As soon as you hit arm, and this is universally true of pretty much all contrast injectors, there's 1 or 2 weird ones that don't do this, but for the most part, as soon as you say arm, which means when we arm it, we're ready to fire. A message will pop up saying, "Have you checked for air?" Now, obviously, I have nothing but air in my syringes, but if I hit yes, it's like, all right, here we go. And then there's the flashing lights that indicate, all right, when you hit the inject switch, we're going to start injecting. Now, for this 2-phase shot, for CT and MRI injectors, you don't have to hold down the inject switch. You just hit the button and it goes. So we're going to start the injection. Contrast goes first for about 4 seconds. Well, exactly 4 seconds. Then it goes automatically switches over to the second phase and does the same thing for the second. So that's a 2-phase injection. All right. Any questions on that? Most injections, maybe all injections are multi-phase or multi-level injections. I don't think, because we buy our contrast injectors we use for training, we buy them used, and we always get them, and it has all the protocols stored in memory, so I can see them. I've never opened up a protocol stored in memory that we've gotten from a real hospital, and it was just a single phase. It's always 2, 3, or 4 phase shots all the time. One time though, when I was teaching X-ray with Ditech, we bought it was a CR reader, an old Kodak CR reader, and it came straight from the hospital, and it still had all the data in the CR reader system, and the patient and the MRNs, the medical record numbers, the patient medical record numbers were their social security numbers. And there were thousands of them in there with the patient's name. I was like, whoa, this was 2005. So like, the internet was a thing. Like, holy cow. I couldn't believe they're sneezing. I'm old enough. I'm older than I look. I went to college. Anybody else have this? My student number was my social security number. Every single test and quiz that I turned in, you had to write your name and your student number, which was your social security number. This was the 80s. But yeah, so Miami University has just a litany of, they have my social security number and my name. I think that's why they keep contacting me for donations. Hey, yeah, we know you're doing all right. All right, yeah, multi-phase. Now, hold and pause. These are 2 other options that we can put into when we're programming a shot, programming an injection. You can insert holds and pauses. So we have this 2-phase injection right here. Between the 2 phases, I can put a hold or a pause. They sound like the same thing, but there is a difference between a hold and a pause. A hold is a permanent stoppage of the injection. All right. So if I go in here, same patients. So we're going to shoot phase 1, and then let's say phase 2, I want to enter a hold. All right. So then phase 3, we'll go back to our saline, and we'll put 5 and 20. All right. So we hit lock, arm. Yes, I've checked for air. Now, so when I do this injection, it does phase 1. As soon as phase 1 is finished, it goes into a hold state. All right. Now, hold state is, again, it's a permanent stoppage of the injection, and it doesn't start up until the operator actually hits the start switch again. Then it moves on to the next phase. All right. So that's a hold. A hold is a permanent stoppage of the injection until the operator reinitiates the injection. Now, a pause is basically the same thing, but a pause is for a specific length of time. All right. So for a pause, change the hold to a pause, and let's say 4 seconds. Lock, arm, yes, I've checked for air, and go. All right, so a pause, we do phase one. Phase one is finished. It goes into a 4-second pause, yep. And then without the operator intervening, it automatically moves to the next phase. I think pauses are rarely used. I don't ever remember seeing a pause in a stored protocol. It's always a hold, because I don't know why. I'm not sure why you would use a pause, because they almost always go with a hold. They want to pause the injection for some reason, obviously, and they don't want it to start again until they're ready. So they always go with a hold. I don't think I've ever seen an actual pause programmed into a stored protocol. But that's the slight difference between a hold and a pause. All right. Delays. There's two kinds of delays. Well, yeah, two kinds of delays. They go by 3 names, which it'll make sense when I get to it. So the contrast injectors, CT and angio injectors, can actually be electronically interfaced with the imaging system. So the imaging system and the contrast injector are talking to each other. What makes that nice is, without getting too much into the weeds about it, now, because if you think about it, I have a start switch, I have an eject switch on my injector, but I also have an exposure switch with my imaging system, whether it's CT or an angio injector. So there's 2 buttons that we have to hit, all right? If the 2 systems are interfaced with each other, it can be set up so that I just hit one of the 2 buttons and it controls both, all right? So I've just hit the inject switch and it'll start the imaging system as well. The operator doesn't have to worry about doing both buttons, okay? So, and that's called ISI, imaging system interface. It's very common among CT and angio injectors. MRI injectors, and I assume it's just due to the nature of an MRI system, MRI injectors don't electronically interface with imaging with the MRI injectors. It's not an option for them, but CT and angio do. So yeah, what makes that nice is the operator just has to hit one button and they both go. Don't have to worry about hitting 2 buttons. So that brings us to our delays. Oftentimes, most of the time, they don't want both imaging and injector systems to start at the same time. They want one to start, give one a head start, and then the other one to go on after that. So there's something called injector delay, which is exactly what it sounds like. We can set the injection up so that the injector starts 1 or 2 or 3 or 99 seconds after the imaging system starts, okay? And then the opposite of that is we want the injector to start, and then so many seconds later, we want the imaging system to go, all right? Now that goes by 2 different names, all right? So it's 2 different kinds of delays, but 3 different names. So if I want the imaging system to be delayed, the start of the imaging system to be delayed, for CT and MRI injectors, it's called scan delay because it's called a CT scanner or an MR scanner. But for angio injectors, it's called X-ray delay because it's actually an X-ray system. Same exact concept, but it's just 2 different names. Any questions on this? Simple concept? Yeah. All right, KVO is just what it sounds like. Well, I shouldn't say that. KVO, keep vein open. What can happen is if there's an IV needle, angio injectors don't have this function because angio injectors, that's the one with the catheter. They don't have this issue with catheters. I'm not 100% sure why, but I guess because the procedures aren't nearly as long. But this is only a CT and MRI thing with the IV needles. If there's not an injection through an IV needle for prolonged periods of time, a blood clot can form at the end of the IV needle and basically start to partially occlude it. To keep blood clots from forming at the tip of the IV needle, what they can do is they'll turn on the KVO function, the keep vein open function. And what that does is some systems do it a little different. What the contrast injector do is every 15 or 30 or 45 seconds or whatever, it'll just do a little 0.1 milliliter injection, just a tiny little drop, shoot it out just to keep the tip of the IV needle clean. One injector model, the only one I know of, it'll do a constant trickle of contrast, just like 0.25 milliliters per second, a constant trickle of contrast out the IV needle just to keep it open. That's a very old model. I don't think anybody does that anymore. That was an Envision. Yeah, that's the KVO function. IV needle or infusion pumps have that KVO feature to them. Some contrast injectors do as well. And the test injection. Again, this is for CT and angio injectors. Catheter or angio injectors don't do this as well. When you insert a catheter, it's more like a surgical procedure. It's not something just some phlebotomist does. All right. But when it comes to when it comes to CT and MRI injectors, they're literally putting an IV needle into the patient's hand or elbow. Then what they want to do is they want to make sure that I mean, every time you get blood drawn or something like that, you know, they'll put it in and they'll make sure that they've hit the vein and stuff like that to start drawing the fluid out. For CT and MRI procedures, same thing. They'll go in and they'll hit the vein, but before they go shooting 50 or 100 milliliters of fluid into that vein, they want to make sure they got the vein. So what they'll do is they'll set up what's called a test injection. Now, a test injection is going to be a very low flow rate, low volume injection, typically 1 milliliter per second. It'll be just a few milliliters of fluid. And so the test injection, you guys will see here. If you're going to do a test injection, remember, this thing is capable of shooting multiple phases. If you're going to do a test injection, you have to do it on the first phase, obviously. We're not going to do a couple phases and I'm like, hey, let's check that needle placement on the third phase. So a test injection, so when I hit this little arrow here and it brings up my first phase line, the options over here are test inject, contrast, flush, a mixture of the two, pause, hold, and so forth. So this test inject function is available on the first phase. And you'll notice here, it's blue, a flow rate of 1, a volume of 20. It's not normally 20, I put that in there. And then this little line here, and again, this is universally true. This little line here down underneath that phase says test injection. That means that indicates a hold. So what's going to happen is, we do our test injection, the system automatically goes into a hold. And we make sure the patient's hand or arm didn't bubble up with fluid underneath the skin. That means we missed the vein. If we're good, then they hit the start switch and it moves on with the rest of the injection. All right, if you'll look here, let me go to phase 2. I don't know if you can see this, but phase 2, that test injection option is not an option. It's not there because after phase 1, test injection only an option on phase 1. It's not available on any other phases. Make sure I'm not missing any info. Only use on CT inject. I'm wrong. That's CT and MRI. Perform with the operator at the patient's bedside. Yep. All right. And so one of the other safety features here. All right. So let's say we're all hooked up to my patient here. These buttons right here, the enable button, forward, reverse, and manual knobs, these are used to load the syringes with the fluids. So you'll notice here, my green side and my blue side, I have these forward, reverse buttons right here. Okay, this is how we electronically move the pistons up and down. And then both sides also have a manual knob down here if I just want to manually move the piston forward, reverse a little bit. Now, you also notice that when I hit a button, let's say we go forward, nothing happens, right? And that's a safety feature, because if the patient's actually hooked up and everything and I go to tilt the injector or move it around or something and I hit a button and the piston moves or retracted, then we've just done something to the patient. So none of these buttons work until I hit that button right here. It used to be, I feel, this button right here, on the original version of the Stellant, it said enable, okay? And then somewhere down the line, they're like, I guess we have to call it the move piston button because people are confused by it. Yeah, so now it says move piston. So, yeah. So now when I hit the move piston button, it lines up real bright so the operator can see, all right, now if I touch the forward reverse button, that will move the piston. And then after about 5 seconds, if I don't touch anything, it goes out. Yep. So when we hit the move piston button, now my forward and reverse buttons are all active. And they're variable speed, slow, fast, forward. Same thing, reverse, fast, not real fast, but faster than slow and things like that. Or you have your manual knobs where you can just manually push the fluid backwards and forwards. So that's the purpose of the enable button, to prevent accidental movement of the piston if we're actually hooked up to a patient. And then, like I said, I just demonstrated the forward and reverse buttons and then the manual knobs. These are used for filling and priming the syringes and the connector tubing. Armed light, I don't remember where this ends. The armed light, you guys saw that. So if I hit arm, lock, arm, yes, right here. There's every injector, there's when you arm it. So now there's going to be some visual indicator, some lights flashing or turned on permanently. That's an indicator to the operator. All right, so we're ready to shoot now. When you hit the start switch, we're actually going to inject. It's another safety feature letting everybody know, all right, we're primed and ready to hit. So that's the armed indicator light. Every contrast injector except the ASIST has that. Is that the end? Is that the last page? Yes, it was. All right. That's the gist. That's the basics, the very basics of every contrast injector. Anybody have any questions on anything? Well, we are located in I live in Northern Ohio, but we don't do classes there. I mean, not as a rule, but how we do it, we'll come to, if somebody has a certain amount of training they need, we just come to your site, come to your city, and then we tell the world, hey, there's a class in Denver. Like the class we have coming up, we're in, where am I? I was just in, where was I? I was just in Nashville. I'm going to be in Omaha in the next month. I'm going to be in Omaha, New Orleans, and somewhere else. I forget where, teaching a class. Yep. So we'll say, we have a class the week of March 10th in New Orleans. We tell the whole world, and then people sign up. We do limit our class sizes to 12 max. But we don't do just one injector model. Like, we don't do like the Stellant on Monday and the Provis on Tuesday. What we'll do is, depending on the size of the class, we'll set up 2, 3, or 4 different injector models, and we'll break the students up into small groups. So we have one group on model A, group on model B, C, and D, and then the next day everybody comes back and we just rotate them to the next model. Yep. And it's typically 1 day per model. So if you're signing for 2 models, and it doesn't matter which 2 models, we don't say, well, you'll have to come in on Tuesday and Thursday. We don't do that. Whatever models the students sign up for, we make sure everybody starts on Monday and they get those models in consecutive days. Yep. I don't like to do it in the hospitals, but yes, often hospitals do it. If they insist on doing it in the hospital, which sometimes, rarely, but sometimes they do want to do it in the hospital, which I hate doing in the hospital, only because I don't have the BMED's full attention. If I'm in their workplace, I got to go to OR. Part just came in. I got to. If we're just 2 miles down the road, they're a captive audience. Yeah. Oh yeah. Yeah, so the class consists of there's operation training, or there's introduction to contrast, which is this, and model specific operation training, and all that is available on our website. Anybody, you don't even have to be signed up for training. Anybody can go to our website and take all those courses for free. We have 6 or 7 different model specific operation training classes that we have, and it's you watch a series of videos, answer quiz questions, you get 75% or more, you can move on to the next set of quizzes. Depending on the model, it's either 3 sets of quizzes, 3 or 4 or 5. Well, the Stellan has 6 quizzes because there's just a lot of information with Stellan. I try to keep the videos to like 3 or 4 minutes and then answer quiz questions. And then the part that you're paying for is the maintenance training. And the maintenance training is, we have a software program that takes the BMET through the entire PM procedure, literally step by step with videos. It's a software program. You watch the video, you do what I did on the video on the machine, document the results on the screen, move to the next screen. It takes you straight through the entire BMET or the entire PM procedure with very detailed videos. Because I was Air Force, and I know there's a lot of Army BMETs out there. You need a lot. Any Army BMETs? I should have asked that first. No. We don't go in a lot of detail on a lot of repairs, but we do cover repairs in the class. For each model, we'll have 2 or 3 or 4 or 5, depending on the model, most common issues that they will run into. And we do have a troubleshooting tab in our software that is model specific as well. Now, MedRad is obviously the biggest one. They'll have they have error code, they have error messages in their service manuals, but they don't publish any of their error codes. And over the years, we have literally collected hundreds and hundreds and hundreds of their error codes and error messages. Those are in the software. So our software has tons of extra error codes and messages that the OEM does not publish, and a lot of them actually have how-to videos with them as well. Not all of them, but a lot of them. We're actually, it's gotten to the point, I need to get it out of the software. I need to put it on the cloud, come up with an app or something, because every time, I'm not a software programmer, I hired a company to make all the software modules for the MIST software. But every time I need to make a change to it, it's like $2,000. And then I got to tell everybody, hey, we got a new version of software. And like only like 50% of the students do that. They'll respond, yeah, send it to me. So then like, for the next 3 years, hey, I need this. Yeah, it's in the software. Oh, I'm still on this software version. It's like, okay, we need to upgrade you too. But the only thing really that gets changed on a regular basis is I'm adding error codes and error messages, and to do it in the software is a pain. So I got to come up with some app or a website or something that my students have that they can log into whenever they want. But not to complain, but BMETs are the worst at reading their emails. I swear to God, it's like any BMETs in here? They're like children. I can't tell you, like we just had, because the Stellant Flex, this is the Stellant, we just had the new Stellant Flex, and everybody in the world is at, you have the Stellant Flex, Stellant Flex. We got the new Stellant Flex about a year ago, and I told everybody about the new Stellant Flex. And I used to have this when I first sent the email out, okay, here's how you add the Stellant Flex module to your MIST software. And it's easy, but I thought, I'm gonna go into details, like 10 steps on how to add it. Man, I'm getting calls, 20 calls a day. Hey, the videos aren't showing up. I was like, that's because you didn't get past step 1. They installed it into the MIST. They installed the new module in the MIST, but there's like other things you got to do to make it, so it works for you. And they do the first step and they're done. And they're like, so I mean, I literally made like 2 steps, and I put in big bright red letters. First, do this. Don't stop here. Go to the next line. And there's literally 2 lines. And I still like 1 out of 10. Like, hey, the videos are played. It's just, man. All right. We do offer tech support. We offer tech support. We don't sell parts. I didn't want to get into parts because that was just a whole nother thing when I first started this. I stayed in training, but I did partner with one other company, and that company ended up becoming a company called Injectors Support and Service, which if you're in the injectors at all, you're familiar with them. So yeah, you can call me up for tech support, but if it turns out that we figure out, yeah, you need a part, then I'll send you to either Injector Support and Service, and there's 2 other companies. There's a company called Biomedical out of Tennessee, Injector Support, they're out of Orlando, they're out of here, so they'll be here today. They're owned by 626, so their booth will probably say 626, but that's Injector Support and Service. And then there's another company out of Texas called Biomedical. They're the Bracco I mentioned earlier, the Bracco company that specializes in Bracco injectors. They're the Bracco injector company that I send people to, and they all they are all full service. They do parts and tech support and depot repair and stuff like that. They do actually have that capability, but it's never used. It's called the EDA, extravasation detector. Or no, I'm sorry, that's different. That's for the extravasation. They do have air detectors, but they never use them. And here's the reason they never use them. Like infusion pumps have the air detectors. All right. For these, if you're going to make an air detector, you want to make it like super sensitive so you don't miss anything, or like, you can let one get by every now and again. All right. No, you can't do that. The air detector has to be super sensitive. And even with infusion pumps, there are false alerts. All right. It's one thing when it's an infusion pump. All right. No big deal. No harm, no foul. The problem is with these, if you get a false air detection, then we got to start this whole thing over. All the radiation we fired into the patient, all the fluid we fired into the patient was for naught. And you can only shoot so much fluid, contrast fluid into a patient. There's no such thing as too much. So the industry, it's not a written rule, it's an unwritten rule for the most part, maybe not even that, but yes, pretty much all contrast injectors have some form of air detector that can be attached to it. I've never seen one in my life actually attached to one in a hospital. They just leave it up to the due diligence of the operator.